In its final moments, a massive star's surface begins to fracture under immense internal pressure. These hairline cracks, glowing with unstable energy, are the first visible signs of its impending collapse. Stars like this, typically 8 to 20 times the Sun's mass, spend their lives fusing elements until iron accumulates in their cores. Iron fusion consumes energy instead of releasing it, destabilizing the star. The cracks emit pulses of light as trapped radiation escapes, a phenomenon observed in supernova precursors like SN 1987A. This is the calm before the cosmic storm. As the fractures deepen, the star's core, a seething plasma sphere at 100 billion Kelvin, is exposed. This core contains compressed, degenerate matter, where a teaspoon would weigh 5 billion tons on Earth. The escaping energy forms spiraling tendrils, resembling solar prominences but magnified a millionfold. These structures follow magnetic field lines, as documented in NASA's observations of Wolf-Rayet stars. The core's blinding blue-white light outshines the star's outer layers, a key characteristic of pair instability supernovae, where light exceeds entire galaxies briefly. The dying star's immense gravity, now fluctuating wildly, bends space-time itself. Background galaxies appear stretched into Einstein rings, an effect predicted by relativity and observed by the James Webb Space Telescope. This distortion occurs because the star's collapsing core increases local gravity by 40% within milliseconds. Matter near the surface accelerates to 70,000 kilometers per second, creating relativistic effects that redshift light. These warping patterns help astronomers calculate doomed stars' masses, as demonstrated in studies of supernova progenitor SN 2006 GY. Cataclysm arrives as the star splits along its equator, a phenomenon simulated at Caltech using 3D hydrodynamic models. The rupture unleashes neutrinos carrying 99% of the explosion's energy, matching observations from Japan's Super Kamiokande detector. Shockwaves traveling at 30,000 kilometers per second rip through remaining stellar material, fusing atoms into rare elements like gold and uranium. This single event briefly outshines its host galaxy, as seen in the 2016 supernova ASASSN 15LH, which reached 570 billion suns luminosity. The star's final act is a spherical shockwave expanding at 10% light speed, visible for centuries as a supernova remnant. This dissipating energy, rich in heavy elements, will eventually form new stars and planets. Modern spectroscopy confirms such events seed galaxies with life-essential carbon and oxygen. The faint blue afterglow, caused by radioactive nickel-56 decay, matches light curve patterns from Type II supernovae. What remains is either a neutron star or black hole, as detected by LIGO's gravitational wave observations.